So in this video, I'm going to be going over two main techniques for approximating the value of functions when you're given an initial condition for the function and you either have a differential equation or can otherwise determine the first derivative of the function at a particular point. So if you're given the function, you can do that, or even if you're just outright given the value of the derivative at that particular point. So the first technique I'm going to be going over is linearization, in which you generate a line which approximates the values of a function near a particular point. And you can also think of this as the tangent line at that particular point, or as a first-degree Taylor polynomial, which is, and that's another technique of approximations. So how do you do this? The first thing you need to do is identify the initial condition, so a x value and a y value for a particular point, which is going to be the center of your line. Then you need to find the derivative at that point, which will end up being, so that's the slope of the equation at that particular point, and it's going to be the slope of your line. So then using the derivative of that point as the slope of the line and the initial condition as the point, you're going to generate a linear equation in point-slope form. And I always forget the formula, so I just put that there. And so you're going to end up, this is just the general formula for that then. You're just going to have your traditional point-slope form with the point on the equation and the slope of the function at that particular point. And then this is just the way it's commonly written as you solve for L of x. So you end up getting the equation of a line which approximates the values of the function near that point. Okay, so let's go through a practice linearization problem, and feel free to pause here or at any other point before any of the other practice problems to try it on your own first. So when you're given, in this case, we're given a function and a point that it's at, and we're trying to approximate the value at another point. So the first thing we need to do is to identify the initial condition. So in this case, we're given the x value, we're not given the y value, but we are given the function f of x, so we can easily just plug in 5 into cosine of x plus natural log of x to get our value. And in this case, we will need a calculator, so I did that math. So you get the initial condition, an x value of 5 and a y value of 1.893. So the next step is to identify the derivative at that point. And in this case, we're given the function of the derivative. So the first thing you need to do is take the derivative of the function. And you get 1 over x minus sine of x. And then you just plug in the point again, and you get the derivative at that point being 1.159. And again, in other cases, you might be given a differential function, which you can plug in, or they might just give you this derivative at that point. So depending on the problem, you will find the derivative in a different way. So then you just need to generate the linear equation in point-slope form, and I, in this case, just did the simplification in advance, and you can see in the top right of your screen the standardized formula, which you'll use basically every time. So you have the slope and you have the point, so you can just plug in and you get your equation. So then what you do with this is, once you have your linear approximation, is all you have to do is plug in the point that you're trying to approximate for, in this case 6, to get your approximation. So in this case, when you're plugging it into this line, you get an approximation where f of 6 is going to be about 3.049. So another thing that's important to determine is if your estimation for the value of the function is above or below the actual value of the function at that point. So whether you have an over or under approximation. The way that you do this is by looking at the concavity of the function. So if the function is concave up, meaning the second derivative is positive, that means that the slope of the function over your interval is going to be increasing. So the actual change in y over change in x is going to be greater than dy dx at that particular point. So you're going to end up having an under approximation. And conversely, if the second derivative is negative and the function is concave down, that means over your interval, dy dx is going to be decreasing. So the actual change in y over change in x is going to be smaller than your dy dx at that particular point. So your estimation is going to be an over approximation. And you can see that in this diagram. Regardless of whether the function is increasing or decreasing, based on concavity, if it's a concave up, you're going to have an under approximation. If it's concave down, you're going to have an over approximation. However, this can get a little complicated if the concavity changes over the interval, so it's not necessarily just about the particular point. As you can see from this, even though it is concave down at the point where you're taking the linearization, at a point, a potential point later on, it could be an under approximation. So you just need to be careful of if concavity is changing. So the second technique we're going to be looking at today is Euler's method. And basically, as opposed to linearization, we're just creating one line. In Euler's method, you're creating a number of smaller lines which interconnect and each have a slope which matches dy dx at a particular point. So by creating a number of lines which interconnect, you can create a more accurate estimation for the value of a function at a particular point. So the process for Euler's method is a little bit more complicated, so it's best to arrange your data in a table like the one at the bottom of your screen. So the first step is to identify the initial condition given the step size, which is the length of each of your small lines along the x-axis. And then you also need either your differential equation or some other way to find the value of dy dx at your initial condition, and then along the function with x coordinates that are increased by the step size from your initial condition. So if your initial condition starts at x equals 1 and your step size is 0.5, you need to be able to find dy dx at 1, at 1.5, 2, etc. So then you need to find the slope of your approximation at the initial condition using your differential equation or any other way that you can find dy dx, whether dy dx is given by a table or whether you're given a function and can calculate it. So then you multiply this slope, which is the slope of your approximation, by the change in the x value given by your step size to determine the change in y. And that's just simple. Change in x times change in y over change in x will give you your change in y, which is, of course, an approximation because your change in y over change in x is an approximation based on dy dx at that given point. So then you just add your changes in x and y to your initial condition to find the new point, which is an approximated value. And then you can repeat this using this new point as your initial condition until you reach the appropriate x value, and then that will give you the y value of your approximation. And this just shows you that in the end you're going to be getting a bunch of these smaller lines which will closer approximate the value of the function than a linearization. So just to give you a better idea of how this works, I'm going to start off with the simplest possible example, which is just going to be approximating the value of y equals x. So y equals x is the same thing as dy dx is always going to equal to 1. The slope is always going to be 1. And y of 0, of course, is 0. So that's your initial condition. So in this problem, using a step size of 1/2, we're going to approximate the value of y equals 1, of y of 1, sorry. So the way that you do this first is you identify the initial condition, which is given 0, 0, and then you find dy dx, which in this case is always 1, but in a more complicated example will depend on your x and y values. And we have our step size, which again is given, is 0.5. So then to determine your change in y, it's a simple matter of multiplying your change in x, which is your step size, by dy dx, which is going to approximate, in this case, is exactly the slope at that across that interval. So you multiply those and you get a change in y of 0.5. And then it's just a matter of adding those to the initial condition, which is 0, 0, and you get your next point is 0.5 and 0.5. And then you just use that as your initial condition, and you do the same thing with a step size of 0.5. dy dx is 1, multiply those. You get your change in y is going to be 0.5 again. And then you just add again 0.5 and to 0.5 and 0.5 to 0.5. And you get your final answer, which is 1, 1. So the approximate value of y of 1 is going to be 1. And of course, it's also the exact value because the slope doesn't change across the interval. So dy dx is going to exactly approximate the slope. So now for a little bit of practice with this, I've got this one example here. And again, I recommend that you pause the video and try this on your own before continuing. So when you're given this, the first thing, again, you need to do is find the initial condition, which is given as y of 0 equals 1. So x equals 0, y equals 1. So you just put that into your table. And then again, the next thing you're looking for is the step size. And because you're starting at x equals 0 and going to x equals 1, and you're using two steps of equal size, of course, the steps will be a change in x of 1/2. So again, you just put that into your table. And then your differential equation is given there, so you can find the slope at any point. So the first thing, again, you do is find the slope at your initial condition, which is, in this case, that's going to be x plus y, so that's just going to be 1. So, and then that's going to approximate your slope over your interval, so you multiply that by the change in x to get your change in y. Again, that will be 0.5. So then you just add your change in x, which is 0.5, to 0 to get the new x value, which is 0.5, and your change in y, which is also 0.5, to your initial y value, which is 1, to get your new y value of 1.5. So then you're going to be doing this process again to get from an x value of 0.5 to an x value of 1. So again, you just put in your initial condition, which is 0.5 as your x value, 1.5 as your y value. Your change in x is still 0.5. In this case, your dy dx is going to be different. It's going to be 2 when you plug that into your differential equation. So that's going to approximate the slope over that segment of the interval. So then again, though, you just multiply that by the change in x to approximate your change in y, and you get 1. And again, you just add your change in x and your change in y to get a approximation of x equals 1 to be 2.5. So again, in this case, you're seeing that you're having two lines with slightly different slopes, which better approximate the curve than just having one line. So your approximation for x equals 1 is going to be 2.5. So let's just go through one more practice problem, and this is actually the same problem as we did earlier with linearizations. So again, the first thing that you're going to be doing is identifying the initial condition, which is x equals 5 and y equals 1.893. That's given. For the same reasons, you're going from x equals 5 to x equals 6, two steps of equal size, so your change in x is going to be 0.5. So then, again, you have your differential equation, and you just put this all on the table. So your dy dx, which is going to approximate the slope over that first interval at x equals 5, is going to be, and I use a calculator for this, of course, 1.159. And then you do the multiplication. All this can be done on your calculator, and you get your change in y, and then you just add that to your initial condition to get your new value. And then once again, you use that as your new initial condition with the same step size and your new dy dx based on this new initial condition. And you use the same process of multiplying to get your new change in y, and then adding both your change in x and your change in y to your initial condition, your new initial condition, to get your approximation. In this case, we're approximating that y of 6 is 2.916. So what you can see here is that this is more accurate than our linearization. The linearization for this problem gave us an estimation of 3.049, and the real value of the function is 2.752. So because of the fact that there are these multiple lines with varying slopes which more closely approximate the function, you're going to be getting a more accurate answer than with just the linearization. So now let's take a look at a practice AP problem, which I slightly modified, but this is from an actual AP test. And we're going to be looking at using both linearizations, which is the same thing as a tangent line, and Euler's method to do this approximation. So we're going to start off with a linearization problem. And again, I highly recommend that you pause the video and try to work through this on your own before watching me go through it. So once again, the first thing that you're going to be doing, of course, is identifying the initial condition. In this case, it's going to be x equals 1 and y equals 15. And then the slope at that point, which is given, in this case, in a table, and at x equals 1 equals 8. And then it's just a matter of plugging that into the point slope form and developing your linearization equation. And once you have that to approximate it at 1.4, all you have to do is plug in 1.4 as your x value, and you get an approximate value for the function at that point. In this case, that is 18.2. Okay, so we're going to try the same problem with Euler's method. And again, I recommend that you pause the video. So to do this, again, we're doing the same thing of identifying the initial condition, which is x equals 1 and y equals 15. And then to find our step size, we're starting at x equals 1, trying to get to x equals 1.4. And we're using two steps of equal size. So that's going to give us a step size of a change in x of 0.2. So then to find our dy dx and our approximate slope at the initial condition, we're just going to be looking at the table in this case, which tells us that is 8. So then, once again, you just multiply the change in x times your approximate slope, which is change in y over change in x, to get your change in y, and that gives you 1.6. And then it's just a matter of adding that to your initial condition to get your new initial condition of 1.2 as your x value and a y value of 16.6. And then you just use that again as your initial condition. You have the same change in x as your step size. And then you're looking at this new x value, which is 1.2 in your table, to find the new dy dx. And in this case, that is 12. So you do the same multiplication and you get a change in y of 2.4. And then you just add that back to your new initial condition to get your approximation of 19. All right, well, thank you for watching this video. Hopefully it was helpful. Here is just a couple more practice problems with Euler's method if you'd like some. You can also use the same initial conditions and differential equations, of course, to practice linearizations. And there's a link at the bottom to answers with work for the Euler's method aspect of it. So thanks for watching.